So today we're going to be looking at how to make dot diagrams for both ionic and covalent compounds. Dot diagrams, just to kind of give you some context, are a way of representing valence electrons in atoms. On the periodic table they've been annotated. You've got some rudimentary dot diagrams up at the top of each one of the columns or groups. Now we're going to talk about how that can actually be a useful tool in looking at how atoms are combined and put together. So ionic bonds happen when you've got atoms that have a large difference in electronegativity. We talked some about this yesterday. So if you've got a very strong, very attractive atom and you've got a weak atom, the strong one tends to dominate the relationship and can completely and totally just steal the electrons that it needs. Okay? Often these are happening from atoms that are at different ends of the periodic table. So in other words, the metal from the left side is going to form an ionic bond with a nonmetal from the right side. And so the dot diagram of that compound, when we draw it, is going to show a transfer in electrons from the weakling metal to the much stronger nonmetal. Now this next part won't make sense until you look at a few examples. But would you all agree that stealing in general is a bad thing?
Yeah.
It's frowned upon. So when somebody steals, what do you think ought to happen to them? They get in trouble. And that's going to be what happens here. In fact, any atoms that are caught stealing electrons, we're going to lock them up and charge them. Okay? And the way we're going to show that is we're going to draw brackets around atoms that accept electrons. And then we're going to draw in numbers above every ion, positive and negative, to indicate what their new charge is. All charges in a properly done dot diagram are going to add up to 0. And every negative ion in one of these compounds is going to end up with a full set of 8 valence electrons, because that's the whole reason that they're taking electrons in the first place. You remember from the goofy video, chlorine had 7 in her valence shell, but she wanted 1 more to be complete, and once she stole that electron from sodium, she was content. Until they jumped off a cliff. Yeah, that took a turn for the leak pretty quick there. So we say dot diagrams. It is okay when you're drawing dot diagrams to not just make them look like dots. You can use little X's, you can use little O's, you can use whatever little symbols you want to. You can even do things in different color. For a couple examples I'm going to work for you here, don't work these while I'm working them, because I can cheat and move stuff around after I draw it, and you can't do that. We're going to start by taking a look at lithium chloride, example 1A. What I'm going to do is I'm going to put an atom symbol for lithium, an atom symbol for chlorine, and I'm going to look at my periodic table and I'm going to find lithium and figure out how many valence electrons it has. So you locate lithium, it's all the way over to the left side up toward the top. How many valence electrons does lithium carry? Just 1. So I'm going to draw 1 valence electron on lithium. Chlorine is over on the right hand side. How many does it have? 7. And how are they arranged?
3 pairs, 2 and 1.
3 pairs and 1 single. Okay, so I'm going to put pair, 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 single. And does it really matter what side the pairs of the singles go on?
No.
Not really. So, in this reaction, the nonmetal, which is chlorine, is going to steal the electron from lithium. And so when you actually draw it, you're going to draw lithium's electron over next to chlorine. Now I've done it as a red X here. You just need to do it where you can tell that electron did not originally start with that atom. Don't draw yet. Now I told you when anybody steals, we do 2 things to them. What do? Lock them up and charge them. So I'm going to lock up chlorine in brackets, and I'm going to charge her. She stole 1 electron, so she gets a charge of -1. Lithium, on the other hand, because he got rid of that negative electron, he also has a charge. What is his charge?
Positive.
Positive one. And if I look at both charges, what do they add up to?
0.
They add up to 0, and my non-metal ion has how many electrons around it now?
3.
So I did it right. Now you can draw it.
We have to put brackets around the lithium too.
Nope, lithium didn't steal anything.
Lithium got stolen from.
That's right, lithium's the victim here. Domestic abuse. Chlorine's going to jail. Let's take a look at example 1b, magnesium chloride. MgCl2. So again, I'm going to start by drawing symbols on my atoms. So magnesium Cl2 tells me that I'm going to have 2 chlorines. Okay. The chlorines, again, have each got 7 valence electrons, so I'm going to give 7 electrons to each chlorine. Magnesium has 2, right? It has, and they're in a pair, correct?
Yeah.
Okay. And magnesium is in 2s, or the second column of the s block. So, who is going to get the electrons from whom?
The chlorines are gonna steal from magnesium.
Right. One's going to go to this chlorine. One's going to go to this chlorine. Now, both of those chlorines are guilty of theft. So we're going to lock both of them up. Each one of them is going to be charged with 1 count of electron theft. So -1, -1. What is magnesium's charge now going to be?
+2.
+2, because he lost 2 electrons. Total charge adds up to 0. Each negative ion has a set of 8 electrons. We're done. Not so bad, right? If only it was always so easy. We'll take a look at one more example of ionic compounds. I'm going to skip example 1c, and I'm going to go take a look at 1d, which is aluminum oxide. Aluminum oxide, I'm going to start the same exact way, with 2 atoms of aluminum, 3 atoms of oxygen. I'm going to kind of space everybody up so we have a little more room to work here. Let's do the oxygen's valence electrons first. How many does it have?
6.
It has 6. Okay, 2 pairs and 2 singles. So let's go pair, pair, single, single, pair, pair, single, single, pair, pair, single, single. Now, according to your periodic table, how many valence electrons does aluminum have?
3.
It has 3. Right? So where are the electrons going to go?
2 to each.
2 to each, right? Okay. So maybe he gets this one. That's a problem. Go with this one. We'll stop being a jerk. And his will be over here.
Those can both be
Sure, that works for me. And then this one can be paired. So, looking at each oxygen, each one has 8 electrons. They all stole those, so we're going to lock them all up. What's the charge on any one oxygen? -2, because each one took 2 electrons. Okay? What about the aluminums?
yeah, they're +2.
Each one of them lost 3, so each one has a charge of +3. Now, my total positive charges add up to 6. My total negative charges add up to 6. So my total overall charge adds up to 0. All my negatives have 8 electrons. I did it right. Questions? Now, the biggest problem people typically have with doing dot diagrams of compounds is that there's actually 2 different systems of doing it. You've just learned the first one, how to do it for ionic compounds, when you've got a metal and a non-metal. But there's another side to the page. And the other side of the page is all about covalent. So after we've got this written, flip over to back, and we'll take a look at those. So, Let's talk about covalent bonds. Now, when you've got two atoms that have a similar electronegativity and they're both pulling the electrons about equal force, nobody's going to be the outright winner. Nobody's going to steal electrons from anybody else. In fact, they're going to share it. If they have a small difference in electronegativity, like you have between two nonmetals, then they're going to share the electrons. And that's what the dot diagrams are going to show. Now, hear me out. This is super important to remember. If you're sharing, you're not stealing. And if no one steals, then nobody gets locked up and nobody gets charged. Okay, I think that's worth repeating so your brain hears it. If nobody steals, then there's no crime. So nobody has to get locked up and nobody has to get charged. All that's happening here is sharing. So you're not going to draw brackets, you're not going to draw charges. In this case, every atom is going to end up with a full set of 8 valence electrons. Except for hydrogen. We forget about hydrogen sometimes because hydrogen's a little bit of an oddball. Hydrogen is a gas, even though it hangs out in metal country. And hydrogen, because it's so small, it only takes 2 electrons for it to be satisfied, to fill up that first energy. So I'll show you the difference. Again, you may not want to draw this until after I have drawn it and shown you. I'm going to start here with hydrogen sulfide, H2S. Okay, I'm going to start with my atoms. Hydrogen, hydrogen, and sulfur. I'm going to go back. How many valence electrons does hydrogen have? That's 1. So he has 1. He has 1. How about sulfur?
6.
Sulfur has 6, right? 2 pairs and 2 singles. Now they have to share electrons because they're all nonmetals and none of them are really that weak compared to the others, and so they're all going to kind of tug on the electrons together. So instead of stealing, one of the hydrogens is going to get in nice and close and cozy to sulfur and bring its electron along with it. The other one is going to get in nice and close and cozy to sulfur and bring its electron along with it. Now what do you see? This hydrogen here, it brought 1 electron with it, but it's also sharing 1 with sulfur. So functionally, how many does it have access to? It's happy. Same thing with this hydrogen up here. It brought 1 and it's sharing 1. What about sulfur?
It's got the same one as hydrogen.
It has 8, the 6 that it brought, but it's also sharing 2, so it now has a full set of 8, so it's satisfied. In other words, they're sharing pairs of electrons in between them. Now, I'm going to have you draw this in just a minute, but there's another way to show this. Okay, and I'm going to show you both ways so that you recognize them when you see them. This little shared pair of electrons between the sulfur and the hydrogen, we can express that instead of a pair of dots. We can express that with a little dash. That dash is the same thing as that pair of shared electrons. So I can have sulfur bonded to hydrogen, this sulfur is bonded to hydrogen. I do also have to show the other dots, the other electrons in sulfur that are not bonded, like that. Either or is fine, and it's good for you to know how to do both. You can go ahead and draw it. But that dash indicates a shared pair of electrons. It indicates a covalent bond between those 2 atoms. Now let me ask your opinion. Based on what you've seen so far, based on how these atoms are joined in a bond here, versus a couple pages ago, or on the other side of your page, where they were joined because they have different charges and they're attracted that way, which kind of bond do you think is stronger, ionic or covalent? And in fact, covalent typically is. It's much harder to break one of these bonds than it is to break the bond between a sodium and a chloride ion. Okay? with those, like you said in the video, just,
They just jump off the
they just jump off a cliff and get in water, and water is enough to separate them. These, you put them in water, and that's not going to be enough to take them apart. Questions? All right, let's look at dichlorine monoxide, Cl2O. I'm going to do the same thing. I'm going to start. I've got an atom of chlorine, another atom of chlorine, and an atom of oxygen. Okay? Chlorine, we already have seen, has 7 valence electrons. So pair, 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 single. Pair, 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 single. Oxygen has how many? It has 6. Okay? Pair, pair, single, single. So how are they all going to get cozy in such a way to where they all get a set of 8?
Single stove.
Exactly, very good. This chlorine is going to get nice and cozy here. Bring its valence electrons along, all of them. There we go. Same thing with this chlorine here. Glucol. And I'll just and okay. So look, each chlorine has a set of 8. The oxygen now has a set of 8. If I wanted to draw this using my little bonds instead of showing all the dots, I have my oxygen, bonded to chlorine, bonded to chlorine, and then any unpaired electrons or any unshared electrons still have to go in the diagram. So I do it like that. This is a great place for a question.
That green line was left.
Oh, that's just chlorine going sideways. I'm sorry.
Oh, okay.
I'll fix it. Maybe. That'll let me. I'll tell you what. I'll just read it off here. There we go. Anybody else? Now, it's been my experience that the hardest part about doing these is trying to decide which, well, first of all, remembering that there's 2 different systems. The second one, deciding which one you're going to use for a given set of atoms. And so you have to be aware of where different kinds of atoms are located on the periodic table. If it's non-metal to non-metal, they're going to share. It's going to be just like this. If it's a metal with a non-metal, then you do the ionic bond, which we'll look at in a minute. Questions, anyone? Okay, well, I think I'm going to stop talking for the day.